I wanted to show you in a video, essentially lay you the groundwork of the topic of Fourier optics. And I'm doing this because I don't think it's the best use of our time in class to go over sort of the derivation and the motivation behind it. Rather, I can show this to you now and you can go through it more or less at your own pace. And we can focus on working practical examples in class, which we will do on Monday. So I wanted to just lay the groundwork for that. And let's just start way back with the idea of maybe a little oscillating charge or a little point source of light. So here's something right here that is either emitting light or is a source of electromagnetic radiation. And we know essentially what's going to happen is that what we're going to get propagating outward are going to be these spherical waves, and they're going to all be propagating radially away. And if we look at a point over here, what you find, if you're interested in the electric field at, say, point P, due perhaps to some oscillating accelerating charge here, or maybe it's just, like I said, maybe it's just a bulb that's turned on. In fact, if you're thinking Huygens principle, this could be not even a source of light. This could just be any place where there is electromagnetic radiation. Again, the idea being that no matter where you look, you can think of any individual point that has light shining through it to be its own source of light, emitting spherical waves. So this doesn't actually even have to be a light source. It could even just be a point at which there is electromagnetic radiation. And if we think then about the intensity of the electric field, some distance, call it r, away from the source, then you know from past experience that the intensity is proportional. If it's an accelerating charge, it'll be proportional to the perpendicular component of the acceleration. There's a bunch of stuff in there. There's some 4 pi's, epsilons, c cubed. I can't even remember all the stuff that's there, so I'm just going to call all that junk c. The important thing to remember is that it's inversely proportional to r. And if you think then about the intensity, which is proportional to the Poynting flux, which itself is proportional to E squared, then you would see that the intensity is proportional to 1 over r squared, which makes total sense when it comes to energy conservation. If you think of imagining a sphere of some radius r, then the amount of energy passing through that sphere ought to be independent of r. So multiplying this by 4 pi r squared ought to cancel the r's and for energy conservation's sake. All right, so that's for an infinitesimal point. I want to adjust this for a moment. I don't think I even need to adjust my picture. I'm just going to erase these things over here. But I want you to change the idea of this picture in your head for a second and imagine that this source of light is now perhaps like an antenna oriented like so, coming out of the board towards you like this. In other words, it's sort of infinite along a line perpendicular to the plane of the whiteboard here. So an infinite line of charges oscillating, or perhaps it's an infinitely long bulb of light that's emitting light waves. You can imagine that in that scenario, it wouldn't be spheres of light that are being emitted. It would be kind of like cylinders. In fact, we call them circular waves because they are essentially the cross-section of infinitely long cylinders coming out of this thing. And if you, again, go through a similar line of reasoning, what you can conclude then is that the electric field at point P is equal to some stuff divided not by r now, but by r to the 1/2. And that perhaps is a little bit harder to visualize or to sort of understand, but if you think again about the intensity being proportional to E squared, if the intensity is now proportional to 1 over r, if you again imagine the energy flowing through some length of cylinder, it'll have some surface area that's proportional to r, not r squared. And so again, r canceling r when you multiply the intensity times an area. That ought to be independent of the radius. This is just a small technical detail that I wanted to get out of the way first. Just bearing in mind that if it's a point source, the electric field at some point P away will be proportional to 1 over R, but if it's an infinite line source, it'll be proportional to 1 over R to the 1/2. This doesn't wind up being terribly important for the points that I'm going to make later in this lecture, but I just wanted to sort of put that in your head now. All right, so why am I going on about this? Well, you've been talking about interference between two sources. You've been talking about diffraction, that is what happens, the interesting patterns that you get when you shine light through a single slit or multiple slits. And I want to take this essentially one step further. We're going to imagine that we have, I'm just going to go ahead and draw myself a coordinate system here. So here's my y-axis. And here's an x-axis, and I'm going to make my x-axis very, very long. So I'm going to give it a little gap here. So here's x. And I'm going to assume that my x positions of interest are going to be so far away from my y-axis, so very large values of x. And then I'm going to imagine, just like I did with the single slit, I'm going to imagine that I have a giant opaque screen at x equals 0 covering the entire YZ plane, where Z is out of the page, okay? So an opaque screen, and I'm going to, just like I've done before with Young's double slit experiment, we're going to imagine that we cut some slits into that screen. Okay, so everywhere I'm drawing a green line here, that means light can't pass through it, it's opaque, but I'm going to cut some slits, and I'm going to do it in what seems like a completely arbitrary fashion. I can have a really big slit up here and a kind of tiny slit down here, it doesn't matter at all. Okay, so then I shine electromagnetic plane waves. So this is a plane wave. I shine light through those slits, and I imagine that at some large distance, call it R, away from the slit plate, I've got a screen. So here's my screen. And I'm interested, essentially what I'm interested in here, is what is the electric field magnitude at some point P on this screen, due to the fact that I'm shining light through these slits. Now this is the same problem you've done before, except with an arbitrary slit pattern, right? Not n slits, not 2 slits, not 10 slits, not even single slits, something different than that, something arbitrary. Again, just for clarity, what I've drawn right here, these are holes in my screen. They're sort of infinitely, you can imagine, so I'm doing this in essentially 2 dimensions, x and y, so I'm imagining that the holes that I'm cutting are infinite in the z direction, so they're actually slits. I can actually make this more general and cut 2-dimensional shapes in the YZ plane, and the analysis is not actually any more complicated at all. In fact, I'll post some notes with the more general derivation, but I want to keep it simple now, just focusing on these 2 dimensions. All right, so the idea is we want to know what the net electric field is at the point P. So I'm going to essentially divide up my holes into tiny little chunks of length dy. And I'm going to define, I'm going to make a couple of other definitions here. I'm going to define the distance from the center of my slit pattern, which is the origin here. I'm going to put a little gap here too, because again, I want to emphasize that this is quite far. I'm going to call this blue vector here vector r. And I will call the distance between this little source of light, call it dy, to point P. So again, there's a gap here. I'm going to call this little r. Just to get my coordinates straight, I'm going to call this location It's 0 on the x-axis, and we'll call it little y along the y-axis. So this dy chunk is at a distance y above the x-axis. I'm going to call point P over here. I'm going to call point P to be at a position capital X, capital Y. Okay? And I'm also going to, while I'm at it, simply define this angle, which is the angle between P and the origin here, to be theta. So if these are big, you can imagine that theta is probably going to be quite small. That is, assuming capital Y is relatively small compared to R, big R. Okay, so the question is, how do we then calculate what the electric field at point P is coming from this tiny infinitesimal point source dy? And I would say that we can write that as, so at P, we can say that the tiny infinitesimal contribution to the total electric field at P due to dy chunk is dE. And as we said before, that's going to be some bunch of stuff that I don't really care about that much over r to the 1/2. Because again, you have to imagine that this source is sort of an infinite line in the z-plane. That's just us, an infinite line in the yz plane. So that gives me an r to the 1/2 down here. And there's also going to be an e to the I kr minus omega t. And it'll be proportional also to dy, because the bigger my chunk is, the more electric field I'm going to have. Okay, so this is an expression. The e to the I kr minus omega t just explains that this is a traveling wave, traveling in the direction little r. So this is like, if I'm, essentially what I'm trying to say here. Let me be slightly more rigorous by making this k dot r. Okay, now what? So the question is, what is r? The magnitude of the green vector in this picture. So what is the magnitude of r? Well, if we look at the picture, it's pretty clear from the picture that it's x squared. So I'm just looking at essentially this right triangle here. So x squared plus this little distance right here squared, which is big Y minus little y squared. All right? So that's the magnitude of my green vector r. Let me just multiply this stuff out inside here. That's going to give me an x squared plus a big Y squared plus a little y squared minus 2 big Y, little y, all inside the square root there. Now what I can do is, if you look at the magnitude of the blue vector now, that's just going to be the square root of x squared. Actually, let me write it this way. R squared is just going to be big X squared plus big Y squared. So what I'm going to do to this expression is I'm going to factor out a big R. So if I take this down, little r, if I factor out a big R, then the x squared plus y squared, if I divide it by x squared plus y squared, that gives me 1. And then I've got the little y squared divided by big R squared. And finally, I've got 2 big Y, little y over R squared. At this point, it's useful to make some approximations. We're assuming that the slit plates, or the distance here, little y, is very small compared to this huge distance here, big R. Right? So right away, we can make a very good approximation that that's almost equal to 0. This term right here is slightly less convincing in its smallness, certainly less convincing than this one. So I'm going to have to keep this one for now. But what I can do is I can do a little binomial expansion, which says that 1 plus epsilon to the n is approximately equal to 1 plus n epsilon plus some smaller terms, right? So we get, as long as epsilon is very small, much less than 1, then this is the binomial expansion. And if I do that with this, then I get r times 1 plus, 1 minus, now the fact, so this is like 1 plus epsilon raised to the 1/2 power, so I've got to bring the 1/2 down, and that kills, the 1/2 kills this too, so I got minus y, big Y, little y, over r squared. So there is my binomial expansion. So this earns an approximately equal to sign. I'm going to put a box around that. All right. Now I'm going to take this approximation. I'm going to plug it in to this expression. So when I do that, I get that dE, the contribution to the total electric field of that small little piece, is going to be C. By the way, let me just reiterate, the assumption here is that y is much less than r, and y is much less than r. It turns out that it's actually still a very good approximation if I drop this term. So I can approximate, this seems a little bit weird, but I can approximate this little r by just big R. But this r, in the exponential, I cannot be so cavalier with, because turns out k, the wave number, k is a huge number. I mean, remember k is 2 pi over lambda, but lambda, for example, for optical light is on the order of nanometers. And so k is on the order of 10 to the 7 inverse meters, right? And so we're talking about a huge number. When you multiply a huge number by even only a slightly varying number, that can make a big difference in the argument for the exponential. So I'm going to keep this term in the argument of the exponential, but I'm going to not bother here. And it's completely sound what I'm doing, even if it seems a little bit creepy. And then, so what do I have as an approximation? I've got e to the I k r, big R, minus omega t, times e to the minus I, big Y, little y, over r squared. Over r, because that r kills one of those r. Okay, did I do that right? And I need a k, sorry. There. And then I've got my dy over here. Okay, so this is my approximate expression now for the electric field at point P, or at least the small contribution. So to get the total electric field at that point, I need to integrate. And in the end, this will be a function of big Y, which remember is the distance from the center along my screen, which is far away, and time. And so that's going to be a c over big R to the 1/2, e to the I k big R minus omega t. And then I have to integrate over all of my apertures. So by apertures, I mean all of my holes, because I have to sum up all of the possible little dy contributions. So I have to integrate over all of my apertures this expression, e to the minus I k big Y, little y, over r dy. All right? I would argue that this is not terribly interesting. This just describes the time oscillation of my electric field at a point big R away, which is at the location of my screen. So this is just the up-down oscillation. I can just as well only worry about the amplitude, so E0, which now is just going to be purely a function of y, to be C over R to the 1/2. So I'm essentially just going to drop this, because the amplitude of this term is always just 1. And so if I'm only interested in the amplitude of the electric field, I don't need to write it down anymore. And so I have to integrate now over my apertures of e to the minus I k big Y, little y over R dy. Now, one more thing that I'm going to do here, just to make my life easier. I'm going to define ky, that is the y component of my wave vector. If you look back at the original picture that I drew, you can pretty clearly see that k sub y, the y component of my k vector, is going to be k times the sine of the angle theta that I defined, which is very close to being, well, actually no, it's exactly equal to being, the sine of theta winds up being big Y, the distance along the screen, divided by R, big R. And if I do that, then I can rewrite this one more time, that the amplitude at an arbitrary point y on the screen is going to be C over R to the 1/2 times the integral over all my apertures of e to the minus I k sub y, y dy. Okay, so this simplifies the look of my integral a bit. Now the next thing that I'm going to do, I'm going to take one more step here. We're almost there, to the point where I want to get you today. I want to define something called an aperture function, which is like curly A. And curly A will be a function of little y, because what it's going to do, it's going to describe the way my holes are positioned on the opaque screen at x equals 0. So it's going to be a function of little y. And we're just going to say that it's going to be equal to this stuff, C over R to the 1/2, times something I'm calling f. Which, just for convenience, I'm going to write as A0 times f, because I honestly don't want to keep writing this over and over and over again anymore. So we'll just call this the amplitude of my aperture function. And f is essentially some number. It equals 1 if the hole is open at that location. It equals 0 if closed. If it's equal to something, or rather, if the hole is like half open and half closed, meaning like it's only letting part of the light through, then it could be between 0 and 1. It could be like 0.5. But the basic idea is that it's somewhere between 0 and 1. 1 if the hole is completely open, 0 if the hole is completely obscured. All right, so that's my aperture function, which means that I can, in the end, I can say that E, as a function of y on the screen, is equal to the integral from -infinity to infinity. I can go from -infinity to infinity now, because anywhere the screen is closed, f is 0. So I'm integrating now over my apertures, basically. -infinity to infinity of a, which is a function of little y, times e to the minus I ky y dy. I'm going to put a box around that, because if you stare at that for a second, I swear to you we have seen this integral before. E of big Y is the Fourier transform of my aperture function. We have found an extraordinarily practical use for the Fourier transform. And I'm going to try, so I think I'm going to stop here at this formula, because this is where I wanted to get you. The pattern on the screen is proportional to the Fourier transform of the aperture function. And you can also remember that the intensity would then be proportional to E squared. So it would be like the square of the Fourier transform. So we're going to see some cool examples of this in class.